Thank you so much for having me and for the organizers for organizing a fantastic conference. My name is Emmet Golden-Marx. I'm a postdoc at Tsinghua University. And today I'll be telling you a little bit about my research that I've entitled Where the Wild Things Are, Galaxy Evolution and Radio Source Properties in the High Redshift Clusters Occupied by Bent Radio AGN or COBRA Survey. And I just want to highlight that this is work that I started as a graduate student at Boston University with Liz Blanton, and I'm continuing at Tsinghua with Xiang Cai. So, because we all know what a galaxy cluster is, I want to dive right into what is the idea of the COBRA survey. So the high redshift clusters occupied by Bent Radio AGN survey is a survey that predicates on the idea that radio AGN are particularly good at tracing galaxy clusters at high redshifts. Specifically, we're looking at bent double-lobed radio sources, so kind of like what Wonky just showed, where we see this canonical U shape. And our sample comes primarily from the VLA FIRST survey, where we have 646 sources at redshifts between 0.3 and 3, 41 of which are spectroscopically confirmed quasars. So to characterize these clusters, we take advantage of optical observations from the Lowell Discovery Telescope and IR observations from Spitzer. Now, before I dive into the results, I do just want to emphasize the importance of a bent double-lobed radio source. As I said, they're shaped like a C, but they're unique for finding clusters because they're shaped like a C. So their morphology implies that there is some dense gaseous medium pushing against the radio lobes and bending them into a C shape. This is generally caused by the relative motion of the ICM and the host galaxy. And at low redshifts, these sources are incredibly commonly found in galaxy clusters. Now at high redshifts, we can take the knowledge that something must be doing the bending to say, well, galaxy clusters are a pretty good idea as what might be doing the bending. So all of our survey is based on the idea that we can use these as signposts to find potential overdensities and galaxy clusters, both lower and higher mass systems. So I've divided this talk into two questions. First, the galaxy properties, and then the radio properties. So we'll start with the galaxy properties, and specifically, are our sources surrounded by red sequences, and what can they tell us about the clusters in general? So because we only have photometry for the vast majority of our sample, we estimated which galaxies are red sequence galaxies based on the color of the host galaxy. So as you can see in these optical images, we have the radio sources shown in blue, and there's a little red circle at the center of those radio sources that highlights the host galaxy. The other red circles are the other red sequence members. So we estimate them being on the red sequence based on having a similar color to the host galaxy, and then we estimate a redshift based on models from EasyGal. Now, because we didn't want to say that the bent source must be at the cluster center, to estimate where the galaxy cluster might be relative to the radio source, I wrote a surface density code that measures the surface density of all red sequence galaxies as a function of the shared field of view. So you can see on these images, these cyan contours, those are a surface density contour that estimate where is the most peak in the surface density of red sequence galaxies. So we use this to estimate here might be the cluster center, and here is where a cluster could be. Now, we do this for all of our fields, but not all of them host clusters. So we limit ourselves by what is or is not a cluster candidate by requiring a 2 sigma over density in a 1 arc minute region when compared to a UDS and SPUDS field background. So we do this to kind of further limit how many might actually be clusters. Now, because we are only looking at photometry, we wanted to further verify that our sources were real and not just line of sight over densities. And we did this by taking advantage of observations from ORELS, specifically their robust spectroscopic and photometric redshifts, as well as their optical and IR imaging, so that we could weight the likelihood that for a given color and a redshift, what was the likelihood that those two matched based on our models. So we did this for both red sequence galaxies, redder and bluer galaxies. And we do this so that we can measure a weighted overdensity, which we've called a combined overdensity, to see, are these structures still overdense in their entire galaxy populations? And what you can see in this image here is that, yes, they do tend to agree. Richer sources in the red sequence overdensity generally have a richer combined overdensity, which gives us more confidence that these structures are real. So in doing this, we've identified 39 high redshift cluster candidates at redshifts between 0.35 and 2.2, with the vast majority falling between about 0.7 and 1.3. So now that I've shown that bent sources are surrounded by red sequence galaxies, I do want to just highlight a few of the properties that we've looked at. In particular, the location of the bent source relative to the cluster center. So in 2000, Sakhalou and Merefeld published a paper looking at low redshift wide-angle tail radio sources in galaxy clusters, and they found that the majority of their sources, 11 of their 16, are within 300 kiloparsecs of the cluster center. Though they do highlight, not shown on this plot here, that one of their sources is at 1.6 megaparsecs. So these sources can be very far away, even though the majority are close to the cluster center. We find similar results with 24 of our 39 sources near the cluster center, implying that though these sources might not be exactly centrally located, they are generally near where we found the overdensity of red sequence galaxies. Additionally, we wanted to look a little bit at the host properties of these galaxies. When we started this analysis, we assumed that the radio source is going to be similar to the surrounding galaxies. So we wanted to see, are our radio sources hosted by BCGs? Are they hosted by bright galaxies, faint galaxies? How do they compare? So as you can see on these color magnitude diagrams, where the red sequence width is shown by these dot dashed lines, some of them are BCGs. Here you're seeing an example of both the host galaxy and it is the brightest red sequence galaxy, but not all of them are. Only 55% of our sources are hosted by BCGs. However, the remaining sources are hosted by bright cluster galaxies. None of them are fainter than the fourth brightest galaxy within our color magnitude diagram. So we're not seeing super faint infalling galaxies as the host of these sources. And as we saw earlier in the week, you can do a lot of science with BCGs. Particularly at lower redshifts, there's been a lot of work done tracing the BCG to the overall cluster population. And we wanted to just do a little bit of a tease of whether we might see that. So for our entire sample, we don't. But if you look only at the clusters where the host is a BCG, so these red points, and then only at the richest system, so above 3.5 sigma in the combined overdensity, we do see a strong trend that richer clusters host brighter BCGs, which could imply which of our systems are closer along, are farther along their evolutionary paths, and closer to being more kind of evolved, older galaxy clusters. So that sort of answers the first question of the galaxy properties. But now I want to turn to the radio properties of these bent radio sources. Now, in particular, with bent double-lobed radio sources, the obvious radio property to look at is the opening angle. Specifically, how wide or narrow are our sources? So we measure the opening angle based on the detections from the VLA FIRST catalog. We identify which of their sources is the lobe, which of their sources is the core. And as you can see in this image here, we measure the angle like this, and we find that 75% of our sources are classically wide angle tails with opening angles greater than 90 degrees, and with only 2 of our sources being classical narrow angle tails with angles less than 45 degrees. So the thing that we were most excited to compare is, does the opening angle trend with the significance? Do we see that richer clusters host narrower sources? And the answer is yes. As you can see from this image, we do see a trend amongst our sample, depending on which magnitude bin you're looking at. We find that richer clusters are hosting narrower bent sources. And this is important because of how the morphology of bent sources tends to be defined. Both Hardcastle in 2005 and Mersoni in 2013 looked at how these sources form and found that the drivers tend to be the ICM density, the infall velocity, and then jet properties. If we treat cluster richness as a proxy for ICM density, we would be seeing that the ICM density is a main driver for our bent morphology. Additionally, we do look at how far, what the offset from the cluster center was to see if that changed these results or could have been a latent parameter, and we did not see any strong trends there. So it would seem for us that the ICM density is the driver here. Now, one of the other properties that we were interested in looking at is, where is the bent radio source? Now, this talk hasn't been so long that I don't remember that I mentioned this a few slides back, but I want to do a little bit more nuance here. In particular, what are the dynamics of the bent source? Is it infalling? Is it outgoing, meaning it's passed through the cluster center, or is it moving at some kind of radial orbit relative to the cluster center, like shown here? So to do that, we quantify this with an infall angle. We measure the angle between the bisector and the cluster center, and we do this to estimate what the radio source might be doing, with the idea that the bent source would be pointing in the direction of its motion. Now, in 2000, in the Sokolow and Merrifield paper, they found that the overwhelming majority of their low redshift bent sources are infalling, and they speculate that this is because bent sources cannot survive passing through a dense and turbulent cluster center, that they would be disrupted. Fantastic. We don't find that. So we measure our infall angle, and we define the things that are classically infalling as having an angle greater than 135 degrees, classically outgoing as having an angle between 0 and 45, and then intermediate as being in the middle. And we find that 11 of our sources are outgoing, 22 are intermediate, and 3 are infalling. So that obviously doesn't really agree with the Sokolow and Merrifield result. And this could be for a number of reasons. It's possible projection effects are causing a lot of problems. It's possible our cluster centers aren't exactly right. It's also possible that our sources are more likely following intermediate paths where they're not really classically infalling or outgoing, but they're moving along a more circular orbit where when they pass through the cluster center, they're not passing kind of dead on through the cluster center. It's also possible, as we heard in Becky's talk, that the ICM is constantly evolving, and that a high redshift ICM looks very different from a low redshift ICM, and these sources may survive passing through the cluster center. So with my last minute or so, I do want to just introduce some of the newer stuff that I'm working on at Tsinghua, which I'm really excited about. And this is looking at the spectral indices of bent double-lobed radio sources, specifically of 21 in COBRA red sequence cluster candidates with LOFAR, VLA FIRST, and VLASS. And I'm just showing an example of one of our canonical bent shapes. So here are some of the first preliminary spectral index maps. I measured as new to the alpha, so that's why we have negative values. And you can see that we see a wide variety in cores. We have some that are very flat, more quasar-like, and some that are almost non-existent, hard to detect. And then we have some lobes that look more like FR2s, some that look more like FR1s. So I'm hoping to use these to probe any asymmetry in the lobes as a possible tease at what might the ICM be doing in interacting with these sources, as well as look at the overall properties of the spectral index as a function of the greater cluster. And just to tease one result here, we do find that in general, flatter spectral index cores are hosted by brighter host galaxies. So we do see that there. And with that, I will leave you with my conclusions. Thank you so much for listening. Hit me up on Slack, ask me questions now. I'm really excited to talk about this stuff.